Welcome to the Wilderness Center's Astronomy Day. This year, our topic is black holes, and I think you're going to enjoy our lineup of speakers today. Our first speaker is Dr. Patrick Durrell. Dr. Durrell is a distinguished professor in the Department of Physics and Astronomy at Youngstown State University, and is also the director of the Ward Beecher Planetarium at YSU. His varied research interests include the study of stars and star clusters in the outskirts of nearby galaxies and in galaxy clusters, often making use of some of the largest telescopes in the world, including the Hubble Space Telescope. He has been a lead author or co-author on over 60 published scientific papers, including work on intergalactic stars, galactic halos, globular star clusters, and dwarf galaxies in the nearby universe. I want to welcome you, Dr. Durrell.
Oh, it's great to be here, Robin. Thank you so much. Okay. Now, just give me a second here while I go back to the beginning here. Well, it's certainly an honor for me to be doing this. I apparently giving the first talk of the whole session. So, well, if nothing else, it's a little bit of pressure being the first one. But I'm going to talk about a topic that has always fascinated people. When I teach my classes, when I ask students, what are the topics you want to hear about in an astronomy course, every semester it's always black holes. And of course, black holes are probably one of the most well-known things in the universe. Most people have heard of them, seen TV shows, they've featured in movies. So what are black holes and how do we find these things? So for me, it's sort of going to be an introduction as to what these things are and maybe give you a hint as to why are they so weird? This little animation is just one example of a scientific visualization of a black hole orbiting another star, and I'll talk about that a little bit. Now, the reason for the title, both big and small, is that there are different types of black holes out there, okay? And at the end, I'll even talk briefly with people who are looking for medium black holes, one in between big and small. But really, to start out, what is a black hole, okay? And you'll see a lot of this. This is a space-time diagram that is often used with respect to black holes, and you'll see a little bit about that shortly. But I start off with saying, imagine an object that is very massive, okay? Let's say 25 times the mass of our sun, okay? Yet so small and dense, okay? The gravity of such a small, dense object is so high that even a beam of light, the fastest thing we know of, can't escape. And that's the speed. The speed of light is 300,000 kilometers every second, or 186,000 miles every second. Okay, so light is fast, but there is a speed limit. But that also means that if you're really close to a black hole, light as we know it, can't get out. Now, when you say something is so massive yet so tiny and light can't get out, it already starts raising red flags. How can such a weird thing even exist? And is it strange? Absolutely. Even for people who are black hole scientists, these are incredibly strange objects, which also makes it kind of fun for, people doing storyline. Some stories I imagine, well, there's a plot hole here. Let's just put a black hole in, it'll fix everything. Oh, all right, that'll do. Okay. And yes, the memes and the jokes write themselves. So, what is a black hole? How do you make a black hole? How do we find these things? Okay, because they are really, really strange. Okay. So in a sense, what is a black hole? Well, one of the main ways to make what we would call a small black hole, using my title, is, imagine an object that has collapsed into such a tiny size. Because the idea of a black hole is not just that it's massive, okay, because more mass means more gravity, but it has to be very, very small and compressed, okay? So it's an object, a massive object that has collapsed and become so small that the escape velocity, and that's this idea of how much speed do you need to leave the gravity of an object, okay? We can do this with spacecraft, okay? I mean, the probes that are going to Mars, they need to achieve escape velocity to leave the Earth's gravity to go to Mars. Well, now imagine something where the escape velocity is so high that, forget about rockets, okay, or even really big rockets, that even light can't get out. But it gets even stranger, because there really isn't any size to a black hole, okay? In essence, what a black hole is think of an object that has all this mass, and it's just collapsed to a point because nothing could stop the collapse, okay? Nothing can stop it. And that's one of the really weird things about black holes. There's nothing to stop the collapse. So you can imagine, again, take our sun, multiply all the atoms in it by 25, and have gravity just collapse it to a point so that it has no size and therefore infinite density. And usually at this point, I would look at my class and go, what do you think? And some of them just stare at you like going, is the class over yet? But most of them will say, wait a minute, does that even make sense? An object with no size and infinite density? Yeah, and that's where, the strangeness of black holes comes in. Now, people always ask, is there a picture of a black hole? So I always show this. We have pictures near black holes, and that'll be stuff you'll be seeing later in this talk, as well as in the future talks afterwards. But a black hole does not emit its own light, at least that we can see, okay? Because again, light cannot leave if it's close enough to a black hole. Well, that last picture, I'm sure, wasn't terribly illuminating. So what about the history? Well, really, the concept of black holes actually comes out of Einstein's famous equations of general relativity, which he published 106 years ago. Okay, and general relativity is the law of the land, really. He himself wasn't that high on the idea of black holes, but other people, understood his equations, said, no, you can actually get a weird object like this. But for a while, and this little strange animation is just the idea of a little black hole, again, where the gravity is so intense that it actually bends the light around it, acting like a lens. Okay, so this is where all the great distortions and things come from. Now, the picture here is as a very famous physicist, a Nobel Prize physicist, John Archibald Wheeler, who actually spent some of his very young years in Youngstown. He was one of the first scientists to start using the term black hole. But it wasn't until the late 1960s. I still don't know who was the first to actually coin the term. I'm still seeing different stories about that. But it was in the late 60s that John Wheeler himself started popularizing this word, black hole, to describe these things. Now, it's not really a hole per se, but what do you call something that is, no size and infinite density and light can't get out? It's kind of a tough thing to try to describe. Now, to understand how we can even look for and what black holes are and how we can expect to find them, I need to talk ever so briefly about Einstein's theory of general relativity. Not in any great detail, because it can get complicated rather quickly. Okay, I still remember my fourth year GR course, we call it GR, way back when, and still try to remember some of that stuff. But Einstein's theory of general relativity was, in a way, to take gravity to the next level. It was a new way to explain gravity. And that is the way we describe gravity now. To him, gravity was not some sort of mysterious force like Isaac Newton had hypothesized centuries before, but it's a distortion of what he called space-time caused by massive objects. Now, space-time is one of those things that people often throw around. Okay, Star Trek is very famous for throwing around the space-time continuum and things like that. But it's just 4 dimensions. It's just the 3 dimensions of space that we're all familiar with, and time is sort of attached to that. Okay, that's really what space-time is. Now, the popular way to describe general relativity is imagine a flat sheet. Okay, think of that as space. Okay, if a beam of light were to go across that flat sheet, it would just roll on in a nice straight line like nothing ever happened, like you would think when you shine a flashlight beam or something. But if there's a massive object, it causes a dent or a pucker in space-time. The more massive and smaller the object, the deeper the well becomes. And one of the predictions of Einstein's theory was that if you're near a massive object, this bending of space-time, notice the light beam here, it actually curves around and deflects slightly. Okay, those of you who've just missed the hole in golf, you've seen this quite a bit. It's not caused by GR, but it's the same kind of thing. Okay, so light can deflect when it's near massive objects. One of the reasons Einstein became so popular is that one of his predictions from 1915 was that, even the sun will deflect light from the background stars by a tiny, tiny bit. And that was one of his predictions. And then people went out in 1919 to watch a solar eclipse and found he was right. They were actually able to measure the effect going, this Einstein guy is pretty good. And that sort of started his popularity way back when. Okay. Now, the more massive and smaller the object is, the more the bending you can get. Okay. Now, in the case of our solar system, it's not a case of a deflection. You can imagine you're in here and going around and around. You're not falling in. That's how the planets orbit the sun. Okay, so that's why I say this is the new way to think about gravity. But this curvature can have interesting consequences, especially when you get to the most extreme versions of gravity near a black hole. Okay, and this is the thing. And actually, I know people at science centers and planetariums who've made things like this. I don't have one to demonstrate to you right now, but they do the rubber sheet, and you just put these masses on it. And again, notice the 20-pound mass causes a deeper bend in space-time, so anything that goes near here will deflect even more. Okay, and the 5-pound mass doesn't do a whole lot. Okay, so this is sort of like the pictorial way to introduce to general relativity. So that's where these diagrams come in, and very often in movies and TV shows, they always throw these in when talking about black holes, or even in the movies. Okay, so here's space-time, and for something like the sun, which is massive but a pretty big object, it's a little bit of a bend. The sun's got some mass after all, and again, you can orbit around like a planet, the Earth, a comet, an asteroid, Pluto. Okay, but if you take the same mass, made it smaller. Okay, the sun eventually, billions of years now, will turn into a white dwarf. Same mass, but it's smaller. So you can get closer and the gravity is stronger, so it makes a bigger dent in space-time. But a black hole is gravity's ultimate victory. Okay, curvature is extreme in a black hole. Matter of fact, once you get close enough to the black hole, you can't get out. And that means light as well. So that's why you often see these sorts of diagrams when you read anything, look online on black holes, you see these a lot. Okay. Now, this is just a still from that simulation I showed earlier. Now, again, with the sun, stars behind it, the light deflects a tiny, tiny amount. You wouldn't notice it. Okay. But if light bends near a black hole, things bend a lot. Okay, no more straight line. They bend a lot, and it actually has the effect of a lens. okay, which grossly distorts things. Okay. Matter of fact, technically is an area outside the black hole, the point, the singularity in the middle, where not that you would ever get this close to a black hole, you wouldn't want to, where you could technically look straight in front of your head, straight in front of you, and see the back of your own head, which is maybe not a great proposition, but so the warping of space-time is very much, gravity. This is just for fun. This is a company, I think it's in Scandinavia, I think, makes this, and I always show this picture because it's a flat carpet, but I always wanted to put it in our planetarium just to see how people would act when they walk on it. So this is more just kind of a fun thing. But for all the weirdness about black holes, okay, mass and no size and infinite density, and light can't get out, they're one of the easiest things to draw. This might be a surprise. Very often when you see pictures, like in one of those memes I showed earlier, they show a black hole like a ball, like a black ball, kind of like the 8 ball in pool, except the 8's been wiped off. Okay, and that's not really, that's not the mass. That's denoting a boundary around the black hole called the event horizon. Okay, which is also the name of a movie. The mass, all the mass of the black hole has collapsed to a point in the middle that we call a singularity. A singularity is just the point where all the mass is, but it's so collapsed, there's nothing holding it up, so it collapses to something with no size. And I sometimes say a singularity is where physicists say, I don't know, what happens inside of a singularity. So all the mass of the black hole is in here. But what people say is the boundary, the size of a black hole, is how far out from the black hole before light can actually escape. And that's called the Schwarzschild radius, named for the scientist who first came up to it. And that's the size of the black hole that sometimes you hear referred to. If you're inside the event horizon, nothing gets out. You don't get out, light doesn't get out. Okay, so that's why, I say here, the point of no return. Okay. So yeah, you don't want to get really close to a black hole. But all the mass is in here. I mean, this is a black hole. It's a singularity. All the mass is there. There's this boundary around it called the event horizon. And that's it. It's kind of easy to draw. Okay. But there's also many misconceptions about black holes. And perhaps the greatest one is, when they're often portrayed in shows, is that that black holes are these giant sucking machines, like a humongous vacuum cleaner or something. And unless you're really close to the black hole, it doesn't act like that. Okay. I mean, it is a lot of gravity because it's a massive object, but it has the same amount of gravity as something with the same amount of mass. Okay. Now, again, if you're really, really close to the event horizon, sure, all bets are off. Light gets bent around. To stay in orbit around a black hole, you'd have to be moving really, really, really fast. Otherwise, you would fall in. But if you're far enough away from the black hole, it acts like anything else with mass. Okay. And I think that for many people, that one of maybe one of the big surprises about black holes. Okay. You have to be really close to it. As a matter of fact, if you took our solar system, okay, and I actually posed this question to my classes. If you were to do a sort of an Indiana Jones, where you come in and you take the sun out and at the same time stick in a black hole with the same mass as the sun. Okay. If you were to do that, the planets, including the Earth, would still orbit in the same amount of time they do now. They wouldn't fall in. They also wouldn't escape. Okay, because when you're far enough away from the event horizon, which for small black holes is a few miles, it acts like any other mass. Okay. So when people hear about, well, there's black holes in our galaxy, are we in danger? Not really. No. Again, when black holes are close to things, that's where we can see the effect of their gravity. But far away, not a bit. Matter of fact, stars and gas can quite easily orbit a black hole, and they don't fall in. You know, we actually see them orbiting around a black hole in the center of our galaxy. So again, this might be one of the main things that surprises people. Well, how do you make a black hole? I mean, they're weird and everything, but how do you make one? Well, there's lots of different ideas how to make, you know, both little and big black holes. And I haven't talked about the big ones yet. But really, it comes down to the life cycles of stars. And this diagram isn't here to try to trip anybody up. There's a lot of information on here. But it's really just to show that stars go through a life cycle. Stars are born, they live, and they die. Okay, so it sounds like a bad soap opera, but it lasts for a really long time. Now, most stars go through sort of a quiet life. They run out of their hydrogen and eventually settle down into what's called a white dwarf. Okay, 99.99% of stars are going to go this way. It includes the sun. But a small, tiny fraction of stars are very massive. When these stars die off, they explode as a supernova, one of the most intense explosions you could ever have in the universe. And when that star explodes, what's left is either a neutron star, which most people haven't heard of, or a black hole, which pretty much everybody has heard of. Okay, so, you know, as someone myself who is interested in stars and the evolution of stars, you know, this is the one way to think about it. It's like, well, how would you make a black hole anyway? Okay, how would something just collapse into a point? It just doesn't happen. Most objects would never do this. Okay, but it is the end result of the explosion of the very few but very massive, the mighty stars that are, you know, present in a galaxy. Okay, so as I put over here, most stars, and that includes the sun, will live billions of years and end up as something called a white dwarf, which is massive and small, but nothing like a black hole. But the highest mass will explode cataclysmically and become one of two things. So really, you know, if you look up at the sky at all the stars, okay, get a nice clear night and look up at the stars, the vast majority of stars you can see will not explode as a supernova. Okay. There's remnants of stars that have exploded. This is a very famous one. This is a Hubble Telescope picture of the Crab Nebula. It's one of the most famous supernova remnants in the entire sky. There's entire scientific meetings dedicated to just this one object. This is the remains of a star that we saw explode almost 1,000 years ago in the year 1054. And what this is gas that is still flying away from the explosion of the star after all that time. Now, in this case, what's left is a neutron star, more specifically a pulsar, deep in the middle here. But some other things that blow up, big stars that blow up, will leave black holes. So there's a way to make them. But it's one thing to say, okay, that's nice for the people who do the computer modeling and we can figure out how stars evolve. And they say, okay, a tiny fraction of stars will explode and become a black, and what's left over is a black hole. But it's a different thing to say, but do these things really exist? I mean, it's really nice to say on TV, oh yeah, these things have mass, but they have no size and they're infinite density. And you just kind of go, really? Okay, this sounds interesting, but are they really out there? Okay, how would you find one? And it's tricky, okay? Because a black hole itself doesn't emit any light, it's not exactly something you can go looking for with a big telescope, okay? So how do you find one? Okay, and this is where one of the things that I enjoy being an astronomer and reading work that other astronomers do, including the talks that you're going to see after mine, is, you know, the kind of, you know, ingenious ways they have of trying to find and study objects. It's not just looking through a telescope. Sometimes you have to use interesting methods to see what's going on. And for a black hole, well, you can't just look up in space and say, hey, look, there's a black hole. But you can go, wait a minute, these things still have gravity. So we don't call them holes, really, because the mass is still there, okay? But if it's near to something, the gravity of the black hole can affect stuff around it, and maybe you can see that, okay? And that's how we look for black holes. Now, I can say quite honestly, the evidence for black holes is extremely strong, okay? Yes, they are out there. Black holes do exist, and we've been finding them for the past 50 years, okay? Even though the concept of a black hole kind of started out almost a century ago, the first good cases of black holes started being discovered in the early 1970s. And the most famous example of a small black hole is something called Cygnus X1, which is kind of a cool name, actually, but it simply means it was the brightest X-ray source in the constellation of Cygnus, which is the Northern Cross, which is a very prominent constellation that you'll be able to see, you know, starting this time of year. Okay. Now, most black holes are not orbiting other stars, but if a black hole were to orbit another star, maybe we can see that. Okay, we can see the effects of that. So the first black holes discovered were in, well, the technical name is high mass X-ray binary star systems, which is really a mouthful. Okay, but what Cygnus X1 is, we can collect X-rays from things out in space. It's one of the brightest objects in the sky if you could see X-rays. But normal stars don't emit a lot of X-rays. And when people located, well, what is at that location? They say, oh, it's a big blue star. And people go, okay, there's big blue stars out there. They don't emit a lot of X-rays. So what's up with this one? Okay, what's so special about this one? Well, they studied the star, the big blue star, and said, it's orbiting something. Okay, so orbiting around like this, we call a binary star. The problem is, the object it's orbiting around, you couldn't see, but was very massive. Okay, I think the latest numbers I've seen is that whatever is orbiting the star at close range is 15 times the mass of the sun. And you can't see it. So that's where people started going, I think this might be one of those black hole things. Okay. Now, some of you may already be questioning, wait a minute, I thought light couldn't come out of a black hole. Where do the X-rays come from? Because X-rays are a form of light. Well, the X-rays don't come from inside the black hole, inside the event horizon. They come from outside. What's going on in this diagram is something called an accretion disk. When you're really this close to a big bloated star, some of the gas will fall in towards the black hole, but it doesn't go right in, okay, like pouring water directly down the drain. It actually approaches it and kind of spirals around it. So the gas will come and spin around very quickly in what's called an accretion disk. Accretion just means to add on, okay? It's this disk of material that's outside the event horizon that makes the X-rays, okay? And how do you get X-rays? Well, there's a lot of this gas that's moving really, really fast, and some of it jams together, makes the gas really hot, and can naturally emit X-rays. So Cygnus X1 is the most famous example of this, but they found about a dozen more of these, you know, because there aren't that many. I mean, this is a special case where a black hole is near another massive star, and you can see the effects of it pulling material towards it, okay? But yeah, we know about, like I said, I don't know the exact number, but perhaps a dozen of these objects are known. But most black holes are not going to be in this situation, but this is a good place to look for them. Okay. I keep showing these diagrams. If you were to go online, look at Cygnus X1, you'll see all sorts of similar things. Big blue supergiant star. Okay. Some of the gas falls in towards the black hole, spins around. The black hole is deep inside here, and material is falling into the black hole. But a lot of it is staying out here and just zipping around at ridiculously high speeds, like this, surrounding the black hole. So again, this is where your X-rays all come from. So for the past 50 years, especially the first, all through the 70s, 80s, and 90s, these were sort of considered the best examples of black holes, okay? But things started to change about 20, 25 years ago. But even more recently, and this is going to be a subject of one of the other talks coming up this afternoon, is we have new ways to find them. And again, as an astronomer, one of the things that fascinates me, I'm not a black hole astronomer, by the way, but one of the things that fascinates me is when people come up with just these incredibly neat techniques to try to find things. It's like they really are detectives thinking outside the box. And it's from that perspective, it's really quite impressive to see. But there's a new way to find black holes using something called gravitational waves, where if two black holes, or they could be two neutron stars, but if two black holes are in orbit and they actually spiral together to make one, that unleashes gravitational waves that can be detected on Earth if you have an extremely precise detector. Okay, extremely precise. I mean, I cannot underline that enough. And people can find them that way. Okay. Just 5.5 years ago, this new era of looking for black holes opened up with the first detection of a black hole merger. And as they merge and merge, these gravitational waves go out through the universe and they get picked up by detectors on the Earth. And the very first one, you could model this, how fast does it happen? How big are the waves? Roughly a pair of black holes, about 30 times the mass of the sun, located far, far, far away, not in our galaxy. Now, as you're going to hear, they're routinely discovering new black holes this way. Okay? I mean, this is one of the neat new things going on. Now, how many of these small black holes are out there? I mean, the ones in X-ray binaries, that's a tiny, tiny fraction. Most aren't in those systems. Well, if you just base it on the idea that high mass stars could explode, we kind of expect millions of them in our entire galaxy. Yeah, that's about how many we expect. Now, the problem is if you say, well, millions of black holes, you go, that doesn't sound very good. Wait a minute. Is there one next door? And the thing I want to remind people, and that's why I say at the bottom, is this a problem? No, it's not. The Milky Way is a very, very big place. Okay, there's about 200 billion stars, normal stars in our galaxy. So some millions of black holes, not a lot. There's a lot of space out there, and this does not suggest there's one even close to us. Okay, I'm trying to remember what's the closest candidate for a black hole. I think it's a couple thousand light years away. Nothing even remotely close for us to care about in that sense. So no, don't panic and don't call anybody to get insurance or anything. Okay. Other ways? Now, what I've been talking about up to now are what we call them stellar mass black holes. Okay. Yeah, they're small ones. They're 10, 20, 30, 40 times the mass of our sun. Okay. Some are in kitchens. But one of the things that people have started to appreciate for about the last 30 years is there's an entirely different breed of black hole out there. And these are what are called the supermassive black holes. Now, these are very different. They're still black holes, but they're an entirely different class on their own. Okay, this is the big black holes instead of the small ones. And the first good case that such a thing existed, we look at this beautiful image of our own galaxy. Now, this is from the southern hemisphere in the outback of Australia, okay, above Uluru. The Milky Way center gets higher in the sky in Australia, so it makes even better pictures than, say, if we, taken one in Ohio. But this is our galaxy. We live in the galaxy, so this is what our disc-shaped Milky Way looks like. And in the middle of the thick part, the bulge of the galaxy, is a strange object that people have been studying for decades. We're just going to zoom in here to the middle of the Milky Way. A long time ago, radio astronomy was a new thing then, detected an extremely bright but very compact radio source in the direction of the middle of our galaxy. And it was given the name of Sagittarius A. No, it was not named because by a Canadian, Sagittarius A. And by the way, I could do that joke. I'm also Canadian. But it was a bright radio source. And then when people studied it with better resolution, they found that there was even a point source within it. So they called that Sagittarius A star. So that's why the name. It's not an asterisk, okay? It's not like it's, like when you look at records by people in football or baseball, It's called Sagittarius A star. And Sagittarius A star, on an infrared image of the center of a galaxy, is right here, located right in the middle of the galaxy. But what is Sagittarius A? It's a radio source, but we don't see anything else there. Okay, there's no star there. There's actually so much dust between us and the middle of the Milky Way. Even with the Hubble Telescope, using optical light, you can't see what's there. But for the last 30 years, astronomers have been using infrared telescopes that can collect infrared light to study the middle of the galaxy. Now, this is an older radio image using the radio telescope, okay, such as the Very Large Array here from New Mexico. This is a radio image of Sagittarius A, okay, this whole complex. But with higher resolution, people say, wait a minute, and I just put a circle there just to put it where it is. There's a tiny little source in here called Sagittarius A star. And things seem to orbit around whatever is at that location. So it's a very well-known object. But what is it? Well, it's long since been suspected to be a black hole. But it's one thing to say it's suspected to be, it's another one to say it is. Okay? Now, before I play this video, I need to preface this because, again, one of the things as an astronomer is it's not just, I'm not only fascinated by the things that I do my research on. And for me, as someone who likes all aspects of astronomy, to me, one of the most exciting results is the study of stars at the center of the Milky Way. The picture on the left here is an infrared picture of the middle. Sagittarius A star is located here, but it's not an actual infrared source there. But there's a bunch of bright stars around it. They call them the O stars, or the S stars, sorry, the S or SO stars. These are high mass stars that move around in the middle of the galaxy, around something we can't see. This image on the right, this is a recent version from the group at UCLA, led by Andrea Ghez. The little star here is the location of Sagittarius A star. There's nothing in the infrared, there's nothing there. But I want you to notice all these objects, this is real data. This is not a computer simulation, this is real data that they've been studying, taking over the last 25 years. And the stars, watch them, you can actually see them move. I can't get enough showing this to people. I have nothing to do with this kind of research, but you can actually see the stars move. Most stars are so far away, you don't see them actually moving. Okay? But here in the middle of our galaxy, these stars, we can see them orbit around Sagittarius A star. The most famous one of these, SO2, which notice its orbit. Its orbit takes it very close to whatever is in the middle of the galaxy, but it comes around every time. Okay? It's orbiting Sagittarius A star just like a comet orbits our sun. Okay? Now, the middle of our galaxy is 26,000 light years away. That's a little bit of ways, okay? It's very far off. So for us to see these stars that are that far away moving in just a few years tells us they're moving very, very fast, okay? They're not just orbiting like the planets orbiting the sun, which is a little on the slow side, okay? And it's all happening in 3 dimensions. This is another simulation from Andrea Gheza's group. These are the orbits of all those objects in 3 dimensions. And notice all of these objects are orbiting something we can't see. Now, for these stars to be orbiting so quickly, whatever is in the middle, whatever they're orbiting around, has to be very massive. Okay? This is one of the properties of gravity. Okay? So whatever's going on in the very, very middle of the Milky Way, it's very massive and very small. Because that star I showed you, SO2, it passes, okay, relatively close to whatever is in the middle, and it comes out every time. It doesn't hit it. Okay? And the speed some of these things go. Okay? SO2, when it passes close to the middle of the galaxy, it's moving at several thousand kilometers a second. Okay? That's like getting from here to LA in a second. It's still going to take hours to park, but you know, the travel time is going to be really, really small. Now, from physics, we can actually calculate the mass. How much mass is this unseen object to make these stars move that fast? Okay? And it's about 4 million times the mass of the sun. So this is a completely different thing than the ones like Cygnus X1. This is a completely different break. We call these supermassive black holes. Okay, and it's an entire cottage industry in astronomy is studying SMBHs, or supermassive black holes. Okay. Now, the importance of this stuff, the reason I spent so much time talking about the one in our galaxy is for many years, this is the best example that black holes existed. And the 2 lead scientists of the 2 teams, one in Europe and one in the United States, that have been studying this and giving you these results, they got the most recent Nobel Prize. Okay, the 2020 Nobel Prize in Physics went to Andrea Ghez and Reinhard Genzel, who both studied independently using large telescopes with infrared detectors to study this. So, it's not that I find it cool. The Nobel Committee thought it was pretty cool as well. Okay, and it's deservedly so. This is neat stuff. It's just from watching how things move. Okay, now, so you're saying there's a big black hole in the middle of the galaxy, and I'm like, yeah, there is. Is it a problem for us? No, no, it's not. It's a tiny feature of our galaxy. Because again, you say, well, supermassive black hole, it sounds impressive, but it's still much less than 1% the mass of the whole galaxy. If you add up all the stars like the sun and all the gas and all the dust, and yeah, even the dark matter, which I'm not going to get into, it's a tiny thing. So it's like a feature of the Milky Way, but it doesn't dominate it. Okay, this is a computer-generated image of what we think our galaxy looks like, a beautiful barred spiral galaxy. The supermassive black hole is deep in the middle, and we're out here about halfway to the edge of the Milky Way, at least the stellar disk of the Milky Way. It's like, well, is that a problem? No. It never will be a problem. Matter of fact, to feel the effects of even this black hole, you still have to be within a few light years of it, not 26,000. So again, think of the supermassive black hole as a feature in the center of our galaxy, but it's not devouring our galaxy or anything like that. Okay? So it's something to keep in mind. But the beautiful thing is, most galaxies now appear to have them. So this is not just a Milky Way thing. Again, since around 1990, astronomers have been studying other galaxies nearby, not with the same precision, but they've been studying other galaxies. And what they're finding is that all big galaxies out there have one. So supermassive black holes, the big black holes, they're out there. And every galaxy seems to have one in the middle. Okay. A very famous one, which again, you'll hear a lot more about later, is M87. This is a giant elliptical galaxy, bigger than our galaxy by quite a bit, in the middle of the Virgo cluster of galaxies. And it harbors a much, much bigger supermassive black hole. The Milky Way is a little one. Okay. We've always known there's a jet of high-speed material coming out of it. We've been observing that for over a century. But deep in the middle, okay, thanks to the people of the Event Horizon Telescope, okay, can zoom right in and see the shadow of the event horizon. That's not the event horizon itself, but a few times bigger than that. This is probably now, people say, do black holes exist? I think most people, you show them this picture and you pretty much get it done. But this black hole is much bigger than ours. Okay, so even the Milky Way's black hole is big, but this one is much bigger. It's about 6 billion times the mass of the sun. And just for fun, here's a little visualization that NASA put out last year that shows light of the accretion disk. But remember, light bends really weird around black holes, and we're just doing little orbits around it. You can see how things bend and distort. Okay, the black hole would be deep inside here, the supermassive black hole. Supermassive black holes sound more dangerous than stellar mass black holes, but they're really not. They're bigger and more massive, but again, if you're not close to it, not a problem. Okay. And again, this one is about 1,000 times more massive than the one in our galaxy. So all galaxies have them. Like I said, black holes are a feature, not a bug. Okay. There isn't a big galaxy nearby that we can study in this kind of detail that doesn't have one. Okay. So what happens when you add a lot of mass? You get all sorts of interesting things happening. Every time I show this slide, I think that I really need to get a cookie. Now again, all galaxies have them. Okay, little galaxies, or at least medium-sized galaxies, have little black holes in the middle, kind of like our Milky Way. Milky Way would be here. And big galaxies like M87 have huge black holes. So they're related. And one of the active areas of research in astronomy is why. So we're still figuring these things out, but we haven't known this except the last 20, 30 years. Now, we've known they should be at the center of galaxies because we observe galaxies far, far away that are active. Galaxies where the middle is so bright it outshines the rest of the galaxy. And the most extreme version of these are something called quasars. This is an artist's impression of a quasar. This is now a supermassive black hole feeding. Okay, it's engorging itself on gas, and it's got the disk of material spinning around it, and it even has these jets of relativistic particles firing out of it. Again, not out of the black hole itself, but the area outside of it. Again, please keep that in mind. This has always been the picture astronomers have had for decades to explain quasars. So we've kind of known they should be out there, but that M87 result and the Milky Way really show you the best evidence that, yeah, these black holes exist, both big and small ones. Quasars look like stars. This is a Hubble Telescope picture of the most famous quasar. And if you take out the starlight in the middle, there's the rest of the galaxy. Okay. Imagine having a bunch of those. Well, I know we're a few months past Christmas, but I mean, all those little fairy lights you can buy. Well, imagine you had a nice field full of those fairy lights, those little tiny LEDs, and then you had a bright navy spotlight right in the middle. It's kind of like what a quasar is. How do you make those black holes? You don't make big black holes the same way you make the little ones. There's no such thing as a 6 billion mass star that explodes as a supernova and turns into a big black hole. So they form in a completely different way. And again, astronomers are still trying to understand, well, how do you make such a really big black hole? Okay. I mean, you can build up. I mean, some galaxies have smaller black holes. If they run together and the black holes merge, you can make bigger ones. But we're still trying to understand that. And right now, a lot of press releases are coming up. People are trying to find ones in between. I mean, you've got black holes that are 20 times the mass of the sun over here. And then you got black holes that are 500 million times the mass of the sun. Or is there anything in the middle? People say they should be, but they're harder to find. But, keep listening, because a lot of stuff coming out on people looking for these things. Two final things. One is, well, let's go be a little personal. What would happen if you fell into a black hole? And I don't recommend this, okay? Because sometimes people say, well, a black hole is a portal to another universe. And it's like, yeah, but you're not getting inside one, okay? Because the gravity near a black hole is so strong, okay? If you were to fall in feet first, the gravity on your feet is so much stronger than the gravity at the top of your head, because strength of gravity depends on distance. You would get pulled, as you get closer to the black hole, you would get pulled out like an intergalactic version of the rack, okay? And Neil deGrasse Tyson and others have popularized the term spaghettification. So first of all, you don't want to go to a black hole. And for a little 3-minute thing, here's a little fun video NASA put out.
So you want to visit a black hole. You've packed your bags, you've updated your passport, and you're basically ready to jump on a spaceship and blast off. However, before you do that, I have just one piece of advice.
Hopefully people can hear this.
Don't. Okay? If you really must go, I suppose you should at least know a few things about black holes before you leave. First, you should know exactly what a black hole is. A black hole is a physical object in space, just like everything else. It's made up of a tiny but massive point where gravity and density are infinite, a line beyond which everything, including light, can only fall into that tiny point, and sometimes some glowing stuff orbiting around it, and maybe some radiation. So basically, here is kind of bad, here is really bad, and here is safe. Also, black holes mostly come in two sizes. Don't ask me why, we still aren't sure. However, a black hole is also not a lot of things. It is not a hole, a cosmic vacuum cleaner, a portal to another dimension populated by unicorns and space potatoes, and absolutely not a good place to vacation. Okay, fine. I guess next you'll need to know how to find a black hole. Though technically black holes could just sneak up behind you, they likely won't. The nearest known one is 3,000 light years away anyway. However, if you were to go looking for one, there are a couple of good ways to find them. First, black holes tend to mess with their environment, so you can sometimes use interesting clues, such as a bunch of stuff orbiting what appears to be nothing. And second, as we mentioned before, there's often glowing stuff orbiting around them, caused by, well, when things get too close. So now that you've found a black hole and clearly aren't listening to me saying not to go, it's time for a few important safety considerations. First of all, the good news is that as long as you stay far away, black holes aren't that bad. However, as you get closer, you need to keep a few things in mind. The radiation near the black hole can be extremely deadly, so the chances of escape get slimmer the closer you get. And if you get close enough, you now have to worry about being stretched into a giant noodle and time getting really weird. So, unless you have great radiation shields, a faster-than-light spaceship, or you're completely indestructible, you should probably just stay away. Well, that pretty much sums up black holes, at least before things start getting really complicated. But before you go for real, please refer to the handy brochure on your spacesuit pocket, since there's quite a bit to remember. Now then, remember your tickets, enjoy your trip, and please, be careful.
So, okay, I just thought I'd end with that. Okay, I do have a final slide, just sort of summing up things. But, you know, really, a little way to sort of end up talking about black holes. Like I said, this was meant as a general introduction to black holes. So if it's okay, people would like me to answer the questions. I got a couple of questions here on the chat. Ooh, that's some good. Okay, we got people right out of the gate with some really good questions. Wow. I have heard of stars that collapse directly to black holes without the intermediate fuss and muss of a supernova. What kinds of stars do this, and what determines this? Again, these would be very, very massive stars. I don't know the reasons behind it, but yes, there are different kinds of supernovae, and yes, they are. I have been seeing some stuff recently about these stars that, for whatever reason, just collapse into a black hole. They don't blow up, and then the black hole forms in there. These are relatively new, and you know, discoveries like this help change our perception. What kind of objects become black holes and how many there are out there. So that's very, very new stuff. Okay, I don't think a lot of stars would go this way, but I don't know the statistics, so I don't want to say too much more. There's evidence for a class of medium-sized black holes. Thoughts on their nature? Yeah, well, first of all, according to many people, they should be there. Because of some of the ideas about making the big black holes is that maybe in the early universe, really big stellar mass black holes could get made. Not today, but back then, maybe you could make even bigger ones. And if you merge some of that together, you start making, you know, things that are not the big ones, but you should be getting something medium-sized. The problem is medium-sized black holes are harder to find. People have, I'm seeing a lot better evidence now, but even 20 years ago, people were claiming, oh, we found an intermediate mass black hole in the middle of a star cluster. And then people look harder and go, I'm not sure you can quite say that yet. So it's sort of been one of these on and off things. So the presence of medium black holes is not as well established as the big and small ones, but they really should be there. From a galaxy point of view, the bigger the black hole, the easier it is to find. So the medium-sized ones would be really difficult to find. And these intermediate mass ones wouldn't normally be orbiting a normal star, a blue star like in Cygnus X1. So you wouldn't find them in exactly the same places. So they're just harder to find, but should they be out there? I would think so. And like I said, I have seen a lot of press releases, groups say, we found a candidate black hole of this mass in this group. I think it's getting, you know, settled that there are some of them out there, but I know some of the earlier ones haven't, but it's hard. I mean, that's the thing. It's not a knock on anybody looking for it. They're really hard to find. And again, astronomers are coming up with new and ingenious methods to find intermediate sized black holes. And again, to me, that's where some of the fun is. It's like, well, we can't find them with this technique. Oh, but I've got this neat idea. We can find them using this. And then when you hear it works, you go, hey, that's pretty cool. So that's, to me, one of the exciting things is how they go about finding these objects.
Dr. Durrell, for the kids in our audience, what made you want to become an astronomer and study the types of stars that you do?
What made me want to become an astronomer? Well, I'm one of these people who I loved astronomy and science when I was a kid. Okay, I was heavily into science. I think when I was 7 or 8 years old, I was heavily into science. I liked rocks. I liked, you know, all these sorts of things. But I saw Saturn through a telescope. I think I was 9 years old, and I was sort of hooked. And by 12 years old, I had said, "Can I do this for a living?" And it's like, "Oh, yeah, I do." So I sort of, you know, maybe it's rare, but I am one of those people who actually decided I wanted to be an astronomer before I even went to high school. Because I'm one of those people, I'm the kid who had the telescope, would go out looking at stuff and enjoying it. So, and it's still that fun kind of thing. It's just that I play with some of the bigger telescopes now and not the smaller ones. But Yeah, I've always loved it. And like I said, the sense of discovery, it's like, even the stuff I do, that, I study stars in nearby galaxies because I sort of got interested in university. Oh, these star clusters called globular clusters are really neat. So I did my master's and PhD theses on those, and still fascinated by them. And it's like, oh, we can learn all sorts of cool things by studying this. So, every year I'm on Hubble proposals to look at star clusters and dinky little dwarf galaxies that are much smaller than the Milky Way. There are lots of them out there, but they're hard to find. So to me, that sense of discovery has always been kind of that fun thing. So I still have that even today. You know, going on, 40 plus years after those 40, 45 years after those early things of astronomy. So
Well,
I don't know if that fully answers the question, but.
Well, when you do your research,
Yes.
you said, like when you're using the Hubble or other large telescopes, there has to be like a cadre of people out there that are assisting you. What other disciplines are necessary for you to be able to carry out your research? Who else do you depend on?
Well, astronomy these days is very collaborative. It's not that common to see an astronomer, hiding away in some office at a university somewhere doing just a project. I collaborate with astronomers all around the world, which is kind of fun because some of these people are my friends. On one project, we have Hubble data for a kind of very faint fuzzy galaxy in the Virgo cluster that I need to get back to working on. And the five other people on the project are friends of mine. So it's kind of cool, email, hey, how's it going? What are you up to? Oh yeah, I'm working on that analysis and stuff like that. So there's still that sense of fun. Because I like working with all these people who are much smarter than me on things. I mean, there are some projects where I'm good at the Hubble stuff, but there are people who study the X-rays and the radio stuff. And I go, I don't know what's going on, but this is kind of neat. And again, there's sort of that sense of fun. But to become an astronomer, you really need to know physics and math. But I do more, I don't do the theoretical stuff like, say, the guys in the Big Bang Theory and stuff like that. I'm an observer, which means I'm into data analysis. I have 3 different projects of Hubble data sitting on my research computer at work, waiting for me to get back to analyzing it. So I use a lot of computer software to analyze images of galaxies, to find out what makes them tick, what kinds of stars they have in them, get distances to those galaxies, and to find new things about the universe. It's like, oh, that's a weird galaxy. Has anyone seen that one before? No. Let's see what we can find out. And that's sometimes how it all starts. And so, yeah, I'm on numerous collaborations. A month ago, I was on a Zoom meeting with collaborators in Switzerland. Talking about one project, and then, and things like that. And it's kind of a neat thing. So most of the support I need are from colleagues who also know their stuff and maybe different parts of astronomy. And we write papers together. We get those papers published. So from a scientific viewpoint, but apart from, other support, yeah, I can't do this stuff. I have students who work with me on projects. They're a lot of fun. My wife is an astronomer as well. She does different stuff, but she's an astronomer as well. And I can't do all this stuff without, all the support people just helping me go through, how do we get this grant? How do we take care of this grant? And I've got people there to help me. Oh, you do this, this, and this. I said, oh, good. I might have a PhD, but it doesn't help for some things. Well, maybe a lot of things. So, so it's really, astronomy is really not, one person standing on some mountain, making some analysis and making some sort of proclamation of what's going on in the universe. It's really not like that. It's a team effort all across the board to do astronomy. And when it's your friends, it's even more fun.
Well, I want to thank you so much for being with us today. You gave us so much good information, and
I hope so.
this was a lot of fun. A lot of fun.
Oh, good. I am thrilled I got a chance. Finally got around to get a chance to do this. And I greatly thank you for inviting me. This is some good stuff. And, if people have questions, other words, they can forward them on to me or what have you. But I wish you and everyone else at the Wilderness Center and everybody online, there's some great stuff coming up in the other talks.